Alright, here we have a slightly more complicated force problem. We've got a frictionless hill, 10 meters high, that's a constant 30 degrees, and I want to find how long it'll take an object to start from rest and slide down to the bottom of the hill. So we're looking for the time, t, that this will take. Now, at first glance, this looks like a kinematics problem. We've got a distance, we're looking for a time, we're going down a hill, but it'll turn out if we try kinematics, we won't have enough information. So, just in the interest of time, I'm going to start with force, because that's where this has to go. And you'll see why the force approach is what we need in addition to kinematics. So let's start with a free body diagram. Now this slightly complicated picture isn't really a free body diagram, so let me make more of a simplified free body diagram. I'll do it over on the side here. So this is my slope, a little steep. That's my slope. Here is my mass, and we'll just call it a mass M. Here is gravity pointing straight down, which is just mg, right? Normal force points straight out of the surface, like that, and there's no friction, so those are actually the only forces acting on the block. So remembering my steps, we do the free body diagram. The next step is just to write Newton's second law. So I've got the sum of the forces in the x direction equals the mass times acceleration in the x direction, and the sum of the forces in the y direction equals the mass times acceleration in the y direction. Now that reminds me, I forgot my axis in the free body diagram. I forget that a lot, but I always remember when I write x and y down here. What am I talking about? I need an x and y axis. So here is a trick that you want to use in slope problems. We are free to pick any axis we want. We always choose axes. And in a slope problem, you always want to point one of the axes in the direction of the slope. So the x direction is straight down the slope, and the y direction is up out of the slope. Okay. The reason for that, several reasons. One reason is if we end up looking for the acceleration, well, we can only either find acceleration in the y direction or acceleration in the x direction. And, well, if the x direction is like off this way, then, well, I don't know, that doesn't make sense. But since the block is accelerating down the slope, if we were to find acceleration in the x direction, that will be its acceleration down the slope. It also just makes the math easier to tilt your axes like this. Okay, so the second step, we're done. The next step is to ask if the sum of the forces is 0, or in other words, if the acceleration is 0. So let's see. Well, in the x direction, no, I don't think it's going to be 0, right? He's certainly sliding down this ramp, getting faster and faster. There's no friction to slow him down. So no, there will certainly be acceleration in the x direction. But in the y direction, well, the mass won't fly up into the air, fly up that way, right? And it certainly won't fly straight into the ground like that. So actually, the sum of the forces in the y direction is 0. All right. Now we have to actually list out those forces. Just an example up here, whatever. In our case, we've got normal force and gravity. Okay, so in the x direction, well, let's check out the y direction for starters first. So we left off 0 is equal to, okay, we've got n in the positive x direction, but then gravity isn't pointing in the x or the y direction, and that's troublesome because we have to get all the forces into our equations. So what we do is we break up gravity into its y and its x components. So this is going to be the force of gravity's y component, and this is going to be the force of gravity's x component. So I can just put that in for now. So normal force was pointing straight up in the positive y direction, but the force of gravity's y component is pointing down in the negative y direction, so minus force of gravity in the y direction. Okay, and now the sum of the forces in the x direction is max, which is, well, we've only got one, and it's the x component of gravity, which is pointing in the positive x direction. So I'm going to put in positive force of gravity's x component. Okay, now the last step is pretty much just to solve what you're looking for. So in this case, what we're looking for is, in the end, we want time. In order to use kinematics to solve for time, though, we need to know the acceleration of this mass down the slope, right? Acceleration goes into kinematics, and we didn't have enough information before. What we were missing was the acceleration, and we can get the acceleration from Newton's second law here. We can solve for ax, then we can take that ax and use kinematics to solve for t. So for now, we're going to set our sights on finding ax. So if I divide through by mass here, I get that ax is equal to the force of gravity's x component divided by mass. That g is a subscript down there. Okay, problem is I made this up, right? I made up this force of gravity x component thing. So we need to know what that actually is. So let's see, what should we have? Let's have another picture. My first free body diagram is getting a little crowded. So I'm going to zoom in a bit here. This is the slope, so its angle is this theta of 30 degrees I mentioned at the beginning. And the mass is somewhere right here, but what I'm looking at right now is the gravity. So the gravity points straight down here, and we broke it up into its x and y components, like that. And so this is FGX, which is the one I'm interested in right now. Okay, so this is a right triangle. We should be able to get the force of gravity's x component, since we know the force of gravity is just mg. These g subscripts are always sneaking up on me. All right, but we need to know an angle in this triangle, right? Now, I'm going to go ahead and let you just prove to yourself, using a few of these triangles here, that theta goes right there. Okay, if this is theta down here, then theta goes up into this corner here, and you can prove it by looking at a few of these triangles. So that means that the sine of theta is equal to gravity's x component over gravity. And so the force of gravity's x component is equal to force of gravity times the sine of theta. So plugging that in up here, I get that ax is equal to the force of gravity times the sine of theta divided by the mass. And don't forget that force of gravity is simply mg. So ax is mg sine of theta divided by mass. Oh, look at that, the masses cancel, and I get that ax is simply g sine of theta. It's a good thing the masses canceled, because, I don't know if you noticed, I didn't actually give us the mass of the object. It was unknown, so it's a good thing it canceled out. And it goes to show you that you really do need to solve these problems in variables, otherwise we would have freaked out that we didn't know mass and given up. But we just kept moving on and hoped it would cancel out, and it did. So now we know the acceleration is g sine of theta. We're looking for the time it takes to get down the slope. So let's draw a picture, more like the picture that we would use for a kinematics problem. Mass starts here, gets all the way to the bottom. We know it's 10 meters high. And that it's an angle of 30 degrees. Let's say theta is 30 degrees. Let's call it h maybe. And, well, it looks like it's going to be a two-dimensional kinematics problem because it's moving diagonally. But if we define our axes like this, then it's just like we did for the free body diagram, then it's just a one-dimensional problem. It's just moving in the x direction, right? So let's list out our kinematic variables. X initial, x final, Vx initial, Vx final, acceleration in the x direction, and time. So we were looking for how long this will take. Alright, so we've done these before, right? Now I just need to see. V initial, well, it's 0. It started from rest. V final, we don't know. X initial is 0 because I placed my origin there. X final, though, would be all the way to the end, or in other words, it would be the length of this slope. And so I wasn't actually given that. I was given the height, though. So I know that this whole distance, which will be the length, the same number as x final. Well, again, I'm going to use sine. The sine of theta in this case is equal to opposite over hypotenuse, h over x. That looks a little bit weird, those variable choices, that h is for height. And so in this case, if I rearrange, I get that x is equal to h divided by the sine of theta. Okay, so I do know x. I did have to kind of figure it out though, right? But I do know x. It's h divided by the sine of theta. Okay, and we know that acceleration is g sine of theta. Okay, so we look at our kinematic equations and pick out the one without final velocity, because that's the thing that we don't care about, we don't know, and we don't want to know. We're looking for time. So it looks like it's going to be this faithful one. X equals x initial plus vx initial t plus 1/2 at squared. Let's see, x initial was 0, vx initial is 0, so that zeroes out that whole term. I'm looking for t, so if I solve this for t, I get t is equal to, the square root of 2x over a. Can plug some things in here. The square root of, so plugging in x, and oh geez, moving on here. I think I'll just plug numbers in at this point, right? So we've got the square root of 2 times 10 divided by the sine of 30 is 1/2, all divided by 9.8 times 1/2, which ends up being about 2.86 seconds. All right. So they will do this to you a lot. They want to hold on to kinematics for a little while longer, so they give you what looks like a kinematics problem, but actually requires using a free body diagram and Newton's second law. It seems annoying and seems like it might be kind of hard to do, but if you think about it, the only thing that's in both kinematics and Newton's second law is acceleration, right? Here's the acceleration up here from Newton's second law, and here's acceleration in kinematics. It's the only thing right now that the two have in common, right? The only other things are force and mass in Newton's second law. So if you have a problem that's part kinematics and part force, you must just use the acceleration to link it. Either you find acceleration in kinematics and plug it into Newton's second law, or you find acceleration in Newton's second law and plug it into kinematics. It's the only thing they have common. All right, so that is about it for this problem. We found the amount of time it'll take an object to go down a frictionless slope, and we didn't even need to know the item's mass. Canceled out. That happens all the time in these problems.